Okay, so now let us look at this problem. We have four vectors, v1, v2, v3, v4. Determine if v3 is in a span of v1 and v2. So this is basically the problem that we just discussed, right? So part A, v1, -2, 1, -3, 6, -1, 0, 1, -2. So set up this augmented matrix trying to see, if we can do something. So we use row 2 plus 3 times row 1 as the new row 2. So this is the row equivalent. So that gives us -1, -2, 1, 0. So this part is also 0. Okay, great. This part is going to be coming into 2. And we have 0, 1, -2. Okay. So clearly, we can, what you can do is you can also do an interchange, right? So interchange row 2 and row 3. So that you have 1, -2, 1, 0, 1, -2, 0, 0, 2. And, clearly, it's not good. Why? Because you only have two variables, right? And then, so this is an augmented matrix, but you have the pivot in each row or in each column. You can see, because if you want this one to be in the span of this, so the last column, it should not have any pivot. Okay, so that's the rule. So the answer for this one, it is no. Okay. In other words, you can also think about this. So the corresponding matrix equation. So the matrix is going to be v1, v2, x equals v3. So this matrix equation is inconsistent. Okay, hence it's not in a span. That's part A. Part B, determine if use the determinant method to check if this is linearly independent. Okay, so we have, so let's list 2, 3, 4 first. So -2, 6, 1, 1, -1, -2, -2, 2, 3 here. Okay, so if it is linearly independent, that means that this 3x3 matrix gonna be invertible. That is, the determinant of this 3x3 matrix, it's gonna be not 0. Okay, so to check that, so let me put this as very clear. If this is 3 vectors are linearly independent, and then you need to have a pivot. After you do the echelon form, you're gonna need to have a pivot in every row, and then that can guarantee that this matrix is going to be invertible, and hence, based on the inverse theorem, a matrix theorem, that is equivalent to see that this determinant, it is not 0. Okay, so that's the logic. So if we want to calculate the determinant of this 3x3, and then what we can do is we can follow it really doesn't matter. We can follow the first row. So it's going to be negative 2 times negative 1 to the power of 1 plus 1, because the index here is A11, times the determinant of this 2 by 2, so negative 1 to negative 2, 3, plus 1, the index for here, this is A1, 2, first row, second column, so 1 times negative 1 to the power of 1 plus 2, and then time the determinant of the sub matrix, which is get rid of the first row, get rid of the second column, which is going to be 6, 1, 2, 3, plus negative 2 times negative 1 to the power of 1 plus 3, because the index here, this is A13. And then times the determinant of this 2 by 2, so it's a 6, negative 1, 1, negative 2. Okay. And then we can do the compute. So this part, it becomes into negative 2, right? So this is a negative 3 minus negative 4, so become into a negative 3 plus 4, so it's 1. So it's negative 2 times 1. For here, this is going to become into minus 1, right? Time, this is 18 minus 2, so it becomes 16, okay? So this piece is going to be minus 2, right? This part is 1, because to the power 4. So this is negative 12 minus 1. So it becomes into negative 12 plus 1, so that is negative 11, okay? Let's put everything together. So this is going to be negative 2 minus 16. This is 2 negatives multiplied, so it's going to be plus 22. So it turns out what we have here is going to be negative 18 plus 22. So it's a 4. If it's a 4, it's not 0. So bingo, we good. So 1, 2, and 3. Excuse me. 2, 3, and 4 are not. They are linearly independent. So yes. Okay. For here is this V1, V3, V1, V2, V3, V4 are linearly independent. The answer is, we can directly give the answer. Clearly it's not. Why? Because as you can see here, V1, V2, V3, V4, the it is going to be the vectors for the R3 here. And as you can see here, so the dimension of the basis, so if you're going to have a basis for R3 here, is going to be linearly independent and a span here, and then the dimension, that part is going to equal 3 here, right? But as you can see, the vector here, it is already greater than, number of the vector is already greater than 3, so definitely it's going to be not linearly independent. Okay, so in other words, if you want to claim a set of vectors to be linearly independent for this R3 here, at most you can have 3. If there is a 4, you out of the game. The other thing, okay, so yeah. Okay, so that's how do we do this problem.